Hi everyone, welcome back. So we're continuing our discussion on thermodynamics. And just to summarize what we saw last time, we introduced work and as it's presented in a PV state diagram. So what a PV state diagram is, it's just a diagram of pressure versus volume for a given process that has some initial and final state. So here, for example, the volume was increasing at a pressure which was not constant, so changing as a function of volume. In this case, the volume is decreasing, we're going in the other direction, but here the pressure is constant. So you could either represent so there are three things that need to be present in a state diagram: initial, final state, and the process. And how you want to represent the direction, it's up to you. You could either write the word initial or final, that should have been sufficient, or just the arrow is enough as well. So we also defined work as the area underneath this plot. So you could see here when the pressure was not constant with volume, you get a pretty complicated area that you wouldn't be able to just directly calculate. You would need to take an integral from your initial and final volume. But if the process is more simpler, like here, the constant pressure, that just becomes a rectangle. So the volume there is P delta V. Also, this minus sign has importance. What it tells us is that when volume, let's say, is decreasing, in this case, the delta V is negative, so our work will be positive. What does that tell us? It tells us that we're putting work into the system. So you can imagine taking a balloon and squeezing it. You're adding energy to the system, you're squeezing it, the force is there that decreases that volume. Where if you let go the balloon, now the air inside the balloon is pushing outwards, the system is expanding, so it's doing work on the environment. So in that case, work is negative because work is being transferred out of the system. So make sure you understand the importance of this minus sign. Okay, let's practice using this equation and trying to figure out work for a given process. So here we have kind of a more complicated process. We have our initial and final state, so it's going this way, and there are various processes that take us from initial final state depicted on this PV diagram. So you can think about it as three separate processes. First, we're at a lower pressure, increasing volume. Then we are at a constant volume with the pressure increasing. And then to get to the final state, again, constant volume, a constant pressure, but volume is decreasing. So the question for you here is the work done in the entire process to the right, positive and negative. So think about the whole process. So the total work, and work, the hint here is work is additive. So you could think about these individual steps and just add up all the work. So what's the work here, here, and there? Think about the signs, and when you add them, will you get a positive, negative, zero total work, or there's just not enough information? So think about it, go back to the previous slide, definition of work. Let's take a look at the answer. So the answer turns out to be positive. So let's kind of look at this step by step. So in the first section, we have an expansion. When we have an expansion, delta V is positive, work is negative. So this is negative work. What about for this process to go from here to here? Well, what's the change in volume here? The change in volume is zero. Or you can think about it, is there any area underneath this curve? No, so the work is zero. So any process that's a constant volume process, there's no work. And if you remember back in a few recordings when we talked about the difference between specific heat at constant volume or pressure, what assumptions did we make for constant volume? We made that assumption that work was zero. So it was only heat that was being transferred in that process. So this is where kind of, hopefully now that makes more sense. Okay, and now let's look at that last process. we have a decrease in volume. So that means work is positive. So we have basically, okay, we can ignore the second section, it's negative, it's 0. But then we have here a contribution that's negative work, and then here we have a contribution that's positive work. So to figure out the net sign, we have to either think about, are the works equal, the magnitudes equal? If they were, then the net would be 0. If the positive is bigger, then the net is positive. If the negative is bigger, the net is negative. So let's think about now the magnitude of the work for the third process. Well, it's the area underneath this whole curve. So here the note is that the work is, so this red area is just that additional area, but the work for the third process, it has to be the red area plus the blue area. So it's bigger. The two colors are mostly there to kind of stress the fact that the work, the magnitude of the work for the first process is just the blue area, where for the third process, it's these two shaded areas, so it's more. So what does that tell us? That the work which was positive in the third section has a greater magnitude. So the magnitude of work 3 is greater than work 1. That's the positive one. So when you sum them all together, you should get a net positive work. So you will do a lot of these types of problems. So you might have look at different steps to get from your initial final step, and you're trying to figure out, what is the amount of work that was done. Also, we'll look at heat and so on. All right, so another important concept that we will be using in the study of thermodynamics, because we'll be mostly looking at gases, and specifically ideal gases, and we get this equation of state. It's called. What equation of state means in thermodynamics is just an equation that relates various state functions. So pressure, volume, temperature are all state functions, and it's an equation that relates them. This should be, or for most of you, I think it's a familiar equation from chemistry. PV equals nRT. What makes the gas ideal? An ideal gas is one where we assume that there are no interactions. So as we've talked about, it's a good approximation for a gas where the inner particle separation is on the order of 10 diameters. We saw the Lennard-Jones potential. We can assume that on average, the particles are not interacting. So then in that case, this model fits that type of gas. So there's some constants here. If you write it in terms of here, PV equals nRT, then N is the number of moles and R is that gas constant. We saw that also previously when we defined our specific heats. R is related to Na Avogadro's number times Kb. So you get this number. Another way of rewriting this is N in terms of big N. The difference between big N and little n is big N is just directly the number of atoms. And then instead of R, you're working with Kb. This is a more common form of ideal gas law that we will be working with. Okay, so our goal will be here is to look at and study various processes and think about, given a process, what is the change in its internal energy, how much heat was put in or added to the system, and how much work was done on the system or by the system. So not all processes have all of these three things present. And we will take a look at these different processes. Okay, so here's kind of an example of the thought process that you will go through when trying to figure out these different properties of a given process. So here's an example of a PV diagram again. So often you will be given, let's say, a PV diagram that demonstrates that process. And our goal is, again, for this process, figure out what is the change in internal energy, how much heat was added or removed, and the work done. So if your starting point is here, what can you figure out? And imagine that, we're doing this very conceptually now, but imagine, you were given the pressures and the volumes and all the information you need to actually get a numerical result, but we're just talking about it conceptually. So what can you do? Well, first, work this term in your first law. You can get directly from the plot. How do you do that? By either taking the area underneath that plot, or if you know the functional dependence of this plot, you will take an integral. So, in Physics 7, we don't do too much calculus, so you might see some very simple integral examples, but mostly we'll only expect you to be able to do areas if it's something simple like a triangle or a line, or just a straight line like a rectangle. Okay, and also make sure that you determine the sign of the work that has to go in here. So for this particular example, we have volume, which is increasing, so work will be negative. Now, how can you get, okay, Q is questionable for now. What about delta U? Can we figure out delta U? So we do know some conditions which are initial and final. We know the initial pressure and volume, and we know the final pressure and volume. So can we get U? Well, yes, but not directly like the way we did work, but kind of indirectly. Delta U, we're talking about gases, so that's just going to be our change in thermal energy. And what is the change in thermal energy? Well, it's related to you can either write it in terms of heat capacity or in terms of total number of modes times 1/2 kb delta T. So it's delta U is proportional to delta T. How can we find delta T for this particular process using just our PV diagram? We can use the ideal gas law, because what does the ideal gas law tells us? It relates pressure and volume to temperature. So if we knew the initial pressure and volume, we can find temperature if we know the number of moles of this gas present. So we can find the initial temperature, final temperature using the ideal gas law, take the difference, and then find change in E thermal as long as we know how many modes we have. How do we find that? Well, we need to know how many moles we have and what type of gas. So this is going to be different for a monatomic gas versus a diatomic gas and so on. So you do need a little bit of additional information, such as the type of gas you have or its specific heat, in order to find delta U directly from your PV diagram. And then finally, Q is normally the last thing you'll calculate. So it's nothing that you get directly from the PV diagram, but by calculating work and then delta U, you can use your first law to solve for Q, which is going to be then delta U minus work. So this is kind of the standard way that you'll approach these problems. Okay, here's some processes. I won't go into too many details, just kind of define them here, and you're gonna have a whole F&T in your discussion lab where you'll look into more depth at each one of these processes. So we've already looked at constant pressure process, that's known as isobaric. So that's when there's, constant pressure just means there's no change in pressure. And then work can be simplified to just minus P delta V. So you no longer have to take an integral. There's also a constant volume process known as isochoric. When the volume is constant, there's no work. So that kind of simplifies, first law simplifies to delta U equals to Q. Constant volume basically means that the only way you can transfer energy is through heat. Delta V implies being 0 implies that work is 0. There's also something known as isothermal process. Isothermal means that the temperature is not changing. So you could still have heat and work being done, but the temperature not changing. So you can imagine two huge reservoirs. By reservoirs, it just means huge areas where the temperature is at equilibrium. So for example, the inside of your house, you're keeping it at a fixed temperature, and then the outside of the house, so heat can still flow from the inside to the outside of your house or vice versa, but the temperatures stay fixed. So the temperature being 0, so this is kind of a subtle point, and be careful. Just because it's constant temperature does not mean that Q is 0. You could still have transfer of heat. What it means is that delta U is 0, because delta U is proportional to the change in temperature. And if temperature is not changing, then that means delta U is 0. So what does that tell us? Is that all the heat goes into work. So if there's heat being transferred, there's work being done. Q is minus W. And then lastly, adiabatic process is one that there's no heat being exchanged. So that's something that's like an insulated container, or perhaps something that's a process that happens very quickly, so there's not enough time for heat to be exchanged. So Q is 0 means that the only way that that the energy of the system could be changed is through work. So delta U is work. So these are some of the kind of standard processes that you'll study in more detail. Okay, here's another question for you. So here we have two separate processes that are performed on the same ideal gas. So same just means, it's, let's say, monatomic, we'll have the same amount with the same initial and final states. So this I and this F, so again, there are no numbers here, but imagine I have the same numbers. So initially we have the same pressure and volume here and here, and the final here and here. But you see that the processes up here and up here are different. The process to get from the initial and final state here and here are different. So kind of based on this information, these two PV diagrams, which one has a greater magnitude of work? So this is a top process, that's a bottom process. Okay, think about this. So just asking about work. So the magnitude of the work in the top process is greater. So let's look at the bottom process. Is there any work being done? The answer is no. There's no change in volume, no work. Is there work done here? Yes, there's a change of volume here. We kind of already looked at this in the first clicker question. There's a, let's think about the sign here. So here we have an increase in volume. What does that mean? Negative work. It has a bigger area than this process, which is the positive work, where the volume is decreasing, so the negative work dominates, has a greater magnitude. So here the work is negative, but here the question was just asking you about magnitude. The point is it's not 0. Here it's 0 and here it's not 0. There is this section that doesn't contribute to work, but the difference between the work done in this process and this process is non-zero. All right, next question. What about which one has a greater magnitude in delta U? So now I'm asking you about the change in internal energy. So think about this. They both have the same. So a more easy, direct way of answering this, delta U is a state function, and state functions do not depend on processes. So it doesn't matter that here it took a very different process to get from initial to final compared to here. What matters for state functions is just the initial and final state. And because they have exactly the same initial and final states, then the difference in that internal energy has to be the same. Or more, mathematically, you could just see, well, initially we have some P and V, we can find T. So here the initial temperature is the same as here. The same for final, same P and V, same T final here. So when you take the difference in temperature, what is delta U proportional to? It's just proportional to the difference in temperature. So they have the same difference in temperature between the initial and final state. Okay, so just kind of giving you a little bit of a more numerical example that you can work out in a little bit more depth on your own. How would we use this ideal gas law to find exactly the change in E thermal for this process? So how would we find delta T? We use ideal gas law, PV equals nRT, so you can solve for delta T. So let's focus on the bottom process. It's easier to think about it because, well, if you just go directly, then there's no change in pressure. I mean, sorry, there's no change in volume, so V is constant. There's only change in pressure over NR. Or you could just, take your initial values of P and V, calculate the temperature, final values, and subtract them. Here it's just kind of skipping a step and going directly to just subtracting the pressures. So I suggest you try this. You can, of course, we need to know the number of moles, so you can assume some number of moles. Okay, so now how do we go from knowing delta T to knowing delta U, which is really delta E thermal, a change in thermal energy? So we need to know what type of gas, monatomic, polyatomic, or the number of particles, which is, really the number of moles. So for example, or you can, of course, write it in terms of the heat capacity. So delta E thermal is the total number of moles times 1/2 kBT, or if you knew the heat capacity, it's the heat capacity times delta T. And what is heat capacity? It's the number of moles times the specific heat. So there's, depending on what information you're given, you have to decide what's the most appropriate or fastest way of calculating change in E thermal. Okay, so you're going to get a lot of practice with more kind of hands-on calculations with this PV diagrams and calculating both work, change in E thermal, and then finally heat. Okay, so another type of kind of special process that we'll look at is what's known as a thermodynamic cycle. So the word cycle means it goes in a circle, and that's basically, it doesn't have to be a perfect circle, but the meaning of a cycle is that it's a bunch of processes that, have to involve both heat and work, where you start at some initial state and then there's stuff happens, but then you return back to that initial state. So cycle brings the system back to its initial state. And there's two kind of main applications of cycles: heat engines, which convert heat to work. So here, because we're returning back to the same state, we don't have a change in internal energy, but we have heat and work being done. So a purpose of a heat engine is you have some heat that puts in and that gets converted to work, or a heat pump where you take heat out from cool to warm by doing work. So it's kind of getting heat out. Okay, so let's look at just kind of an example of a cycle. This is known as an Otto cycle, and I'll tell you next where, what this Otto cycle represents. But let's just think about it more just theoretically. So here's a cycle. Let's say we start at 1, then we go to 2, 3, 4, and back to 1. So again, it's kind of a closed loop here. So looking at this, can you answer what is true about the entire cycle? So not just a particular process, but the whole cycle. What is true about delta U, W, and Q? All right, I suggest you pause it, think carefully. Okay, so delta U has to be 0. Why does it have to be 0? Because we start at some initial state, at some initial, temperature here, and we go all the way back. So there's no change, no net change in state function. So delta U is 0. So that tells us that, without even kind of thinking about the signs, you cannot have, because that tells us that Q equals to minus work. So you cannot have them be different signs or the same signs. I mean, they have to be different. So if work is negative, Q has to be positive because Q is minus work when you solve for that. Okay, but So C is sort of that choice that comes out naturally. Really, one of the choices should have been the other way, like work is positive and Q is negative, but it wasn't that choice. But let's actually convince ourselves that indeed work is the one that has to be negative. And how do we do that? By that same reasoning we used before, which magnitude of work is bigger. So here volume is decreasing in volume. What's the sign of work? Work is positive, and that's the smaller area. These are both zero work. So this adiabatic process, by the way, that's how an adiabatic process looks like. Adiabatic means no heat. This is the one that's the negative work, and it has the bigger area. So the negative work has a bigger magnitude. So in the whole cycle, when you sum all the work has to be negative. What does that tell us? That the heat has to be positive, because Q again is minus W. All right, so here's an example of where an Otto cycle, this type of cycle that we saw in the previous slide, is used to model a real physical system. So this is kind of an idealized way of modeling here a system, which is basically the way engines work in your car, so that it's known as the internal combustion engine. So in reality, it's a little bit more complicated than this Otto cycle, but it's a sufficient model to describe what's going on. And what does this engine do? It converts heat to work. Why does it do that? So we saw in the clicker question that we had an input of heat and output of work. What's the purpose of your engine? Is to use the fuel from the car in order to make the wheels turn, and that exactly what happens here. There's a process of combustion that happens. So heat is being put into the system, which allows this crank here. So there's a little piston connected to a crank, which moves and always in one direction, which eventually is what's making the wheels of your car rotate. Okay, so let's just kind of take a look at, this is just defining one cycle. So when you look at the RPM, revolutions per minute, meter in your car, this revolution is exactly this, describes this one cycle. So that's when your crank goes one revolution around. So normally there are many of these happening per minute. Okay, so what's happening? Initially, this fuel comes in to this chamber. So there's this addition, which is not really part of the cycle, but this is just the fuel coming in. So the volume in this chamber increases. As this volume is increased, this piston is moving. So there's that motion, kinetic energy available to it. So the piston is able to do work on the gas, compressing it. There's no heat being exchanged during this process. So that's described by this adiabatic process from 1 to 2. So that's basically when this crank is coming back up. Now, at this point, this ignites the spark. So your fuel goes through combustion during this process of combustion. So this is from point 2 to 3. Volume is not changing, but thermal energy is increasing. The pressure is increasing. So this is heat being kind of put into your system. Now that thermal energy gives the ability of the gas to do work again on this piston, now pushing it down. So the volume again expands in another adiabatic process when heat is not being exchanged at this point. So this is your gas expanding again. Now at this stage, this excess thermal energy is being taken out through this exhaust. So that's this process where the volume is still staying constant, but pressure is going down as the heat is leaving the system. And then finally, this motion of the crank allows this now exhaust or this air to come out here. So that's this line where the volume decreases. So this is kind of your waste that comes out in the back in the exhaust, and then the whole process starts all over again. So this defines this one revolution of your engine. All right, that's it for today. Thank you for listening. See you next time.